In this session, I would like to demonstrate reaction with an objective of calculating the equilibrium constant, the composition of the reactant mixture when the system reaches equilibrium. Try to look at this problem, and if you try to review, you might have done these calculations in your thermodynamics under chemical reaction equilibrium. So this is a fundamental relation representing the Gibbs free energy change of reaction to the equilibrium constant. So typically we will be able to calculate the change in Gibbs free energy for the reaction based on the Gibbs free energy of formation for various components involved in the chemical reaction. So usually this data is available at 298 Kelvin. So at 298 Kelvin, using this relation, we should be in a position to calculate the equilibrium constant. So this is the Van Hoff isotherm, and under two circumstances, for example, if you assume the heat of reaction is constant, doesn't vary with temperature, though this is an assumption, under these circumstances, when you integrate this expression, you will be in a position to get this relation. We already know how to calculate the equilibrium constant at 298 Kelvin. Now, once we know this, along with the heat of reaction, we should be in a position to calculate the equilibrium constant K1 at any temperature T1, provided if heat of reaction is assumed constant. Normally, this is an assumption. So if this is not valid, what we are required to do? You need to express the heat of reaction as a function of temperature based on the specific heat temperature dependency for all the components. I think you know the specific heat Cpig by R is given by A plus Bt plus Ct square plus dt power minus 2. So integrating that relation, I think you might have already seen this expression earlier in your thermodynamics. You know what is delta A, delta B, delta C, delta T. For example, delta A can be defined as sigma mu I Ai. And we know how to calculate the heat of reaction, at least at a temperature of 298, based on the heats of formation data. So once we know delta HR at a temperature of 298, now if you look at this equation, only unknown happens to be this constant J. So you will be able to calculate J. Once J is known, we should be in a position to calculate the heat of reaction at any given temperature for the given chemical reaction. In the same way, you will also be able to calculate delta G naught at 298 Kelvin. So substituting the temperature, delta G naught and J that is calculated from the previous equation, we should be in a position to calculate height. So once we know this, we will be in a position to calculate delta G naught at any temperature. So once we know delta G naught at a given temperature, we should be in a position to calculate K. This is the case when heat of reaction is dependent on temperature. Now once we calculate the equilibrium constant is related to the mole fractions of the reactant mixture when the system is at equilibrium by this equation. Product of yi to the power of mu I is equal to p by p0 to the power of minus mu into k. And we know how to write yi as a function of xi, where xi is the extent of reaction, mu I is the stoichiometric number. So yi is represented as the initial moles of component I, the total moles m naught. Xi is the extent of reaction, mu I is the stoichiometric number, mu is sigma mu I. So we will be in a position to, if you substitute yi, then the left hand side is going to be a function of only xi. We know all the other quantities. We know the pressure. So we already calculated K at the given temperature. So we should be in a position to calculate xi, and from xi we should be in a position to calculate the composition. In fact, you also saw how to calculate in case if more than one reactions are reaching equilibrium simultaneously, multi-reaction equilibria, though I am not presenting those details in this exercise. Now let us see how to handle this type of calculations by Aspen, carrying out process simulation. In fact, most of the problems you have solved in your thermodynamics course, you should be in a position to solve them here. One small thing that I would like to highlight here, when you write these equations, remember we have been assuming the reaction mixture as ideal. So the moment you assume the reaction mixture as ideal, the enthalpy is only a function of temperature. So in all these cases, all these equations are applicable for the systems which are at equilibrium. Probably in reality this may not be true. So we may have to handle the calculations in the real gas behavior. So the first step in the simulation is to define all the components we are going to handle. C3H8 is getting decomposed into C2H4 and then methane, CH4. So these are the only components we are handling. In case if you want to compare the result of this simulation with your analytical result, you need to assume ideal behavior. But if you want to calculate that under non-ideal conditions, you are required to choose an appropriate property package. For the time being, let me choose ideal, so that you will be in a position to compare the result obtained from simulation with your analytical result or with whatever problems that you have solved earlier. Next, go to simulation environment. Now once you go into this, there are two models which will be able to, using which you will be able to simulate or calculate reactions when they reach equilibrium. Both R equilibrium and R Gibbs. In fact, you can see R equilibrium is going to, it's a rigorous equilibrium reactor model based on stoichiometric approach, whereas R Gibbs is a rigorous reaction or multi-phase equilibrium based on Gibbs free energy minimization. In fact, either of these are going to give you the same result. In order to demonstrate that, I would like to use both these reactor models and try to compare the result. So I'm using a duplicator. I think you know the purpose of this duplicator. Then followed by the two reactor models. The first one is R equilibrium and the second one is R Gibbs. Now let me make the connections, input and output streams for each of these models. Now the purpose of the duplicator is I'll be able to take any number of outputs from this duplicator block, and what the duplicator block does is it copies the input stream information to all the output streams. So instead of defining several streams, if you are able to define the input stream to this duplicator, now for example, if you know S1, S2 and S3 will have exactly the same information as that of S1. That is the purpose of duplicator. So you can see Gibbs reactor has only one output, whereas equilibrium reactor has two. The first one is vapor product and the second one is liquid product. Remember, these two are going to operate on slightly different principles. For example, as you know, the necessary and sufficient condition for chemical equilibrium, you might have derived this relation in your thermodynamics course, is sigma nu I must be equal to 0. That's how it tries to calculate based on this particular equation. Whereas the Gibbs reactor model will try to minimize the total Gibbs free energy in order to calculate both phase equilibrium as well as reaction equilibrium. Try to identify the kind of inputs that you have to specify for both these reactor models as we progress. So go to the next input screen. One more complication in this case is probably you will be in a position to calculate the equilibrium constant, the composition of the system at equilibrium, if you know the temperature and pressure. So here we know at what pressure the reaction is reaching equilibrium, but in order to obtain a conversion of 80% at equilibrium, that means XAE is equal to 0.8, at what temperature the reaction must be able to reach equilibrium. This is of course slightly more difficult if you try to handle this calculation manually. Anyway, let me go back and try to solve this problem. So we don't know the temperature at which the reactor must operate in order to obtain 80% conversion. So this is an analysis problem. So we will try to convert this analysis problem into a rating problem by assuming the temperature at which the reaction is reaching equilibrium. And I think the inlet and outlet, the inlet temperature may not have any effect. So let me presume some temperature, 25 degrees centigrade, maybe 1 atmosphere. This is the condition at which the feed is entering. And we know in the problem statement, pure C3H8 is entering into the system. Okay, so we have defined stream 1. Now we need to define certain information with respect to the blocks. So go to the next input screen. Duplicated, you don't have to give any information. Now we are being asked information with respect to this equilibrium reactor model. See what information is required here. Now the temperature at which the reactor is operating. So as I said, let me presume or assume the temperature as 200. We don't have any idea about this. And the reaction is supposed to reach equilibrium at a pressure of 1 atmosphere, right? So we have defined temperature and pressure. Then next, reactions, say mu, and define the stoichiometry. So C3H8 is decomposing into C2H4 and CH4. So we have defined the reaction stoichiometry. As you can see from this equilibrium reactor model requires temperature, pressure along with the stoichiometry of the reaction. Now, unless and otherwise you know the stoichiometry, you will not be knowing mu I, the stoichiometric numbers, because this model is going to calculate the chemical reaction equilibrium based on sigma mu I. We need to define the stoichiometry. So we have taken care of block B2, which is the R equilibrium. Then we need to define the Gibbs reactor model. So we are, depending on your requirement, calculate. You can choose any one of these options. We wanted to calculate both phase equilibrium as well as reaction equilibrium. Like what we did earlier, let me assume the same conditions so that we will compare the results from both these models. Now you can see in the case of Gibbs reactor model, we are required to identify only temperature and pressure. No reaction stoichiometry is required, right? Okay. So you can see that the required input is complete. So we should be in a position to run the problem. Say next, run the simulation. Now we got to our results. For example, let me see the stream results here. So out of 100 moles of propane that is entering into the system, only 90 moles are coming out. So what is the conversion? Conversion is FA0 minus FA divided by FA0, which is about 9.4%. So by allowing the reaction to reach equilibrium at a temperature of 200 degrees centigrade and 1 atmosphere, we were able to get only 9.4% conversion as per Gibbs reactor model. Similarly, let me also see, and one more thing is, you can see that the output is in the vapor fraction. Vapor fraction is 1. In fact, both input and output at the given temperature and pressure are going to be saturated or completely gas phase or vapor phase. Now let us look at the results of equilibrium model or equilibrium model. Once again, you can see S6, which happened to be the liquid product, is missing. That means you only have the vapor product coming out from even the equilibrium reactor model, which matches with the result obtained from the other Gibbs reactor model. Now let us see what about the conversion. Once again, you can see even this model is giving you exactly the same result as that of the Gibbs reactor model. So depending on your convenience, you can use either equilibrium reactor model or Gibbs reactor model to calculate equilibrium conditions in the case of reversible reactions. But as per the problem, we are supposed to calculate the temperature at which this reaction is going to reach equilibrium such that you will be able to get 80% conversion. Now when we assume the temperature as 200, we only got to 9%. So we can solve this problem maybe by using a design spec. So go back. So you can in fact use the design spec on either of these models. I will be using it on only one of them. Flow sheeting options, design spec. Say new. We have seen this. So what is the defined variable? We wanted to get some conversion, right? So let me define conversion as I have FA0, the inlet flow rate of propane. This is FA0. It's a stream variable. because the input is only propane, we can take the input into this particular reactor, Gibbs reactor is S3. Of course, you can take even S1 because both are going to be same. S3, and the component is methane, sorry, propane. So we have defined this, and similarly, let me also define another, the output molar flow rate of propane from the exit of the reactor. This is also a stream variable. So, like what we did with F0, we can do this also. Now this is from the exit of the reactor, which is S4. The component is C3H. Right? Now the spec, what is the conversion we are looking at? So this is the conventional definition of your conversion, FA0 minus FA divided by FA0. And what is the value that we are looking at? We wanted to get a conversion of about 80%. So give some tolerance. So this is the spec. And in order to achieve this conversion, what is that we are trying to vary? The temperature of the reactor. So this is a block variable. Block is V3, that is the Gibbs reactor model. And the variable is temperature. So we know what should we do? Should we increase the temperature or decrease the temperature in order to get the required conversion? If it is an exothermic, anyway, let me presume that some range of temperatures, 200 to 1000. So we have defined this. Now you can see only block V3, you can see the flow sheet. So this design spec was operating only on the third block, which is the Gibbs reactor model. So as you can see from this, we are reading the value of FMR, the molar flow rate of C3H8, and we are assuming some temperature like 200 to start with. Calculate the molar flow rate of propane at the exit. Now calculate the conversion as FA0 minus FA by FA0. Compare the value with 0.8 that we require. If the requirement is not met, go back and adjust this temperature. So as you can see, every design spec problem in Aspen by default will be solved by this model, by this method, secant method. Anyway, let us look at the results of design spec. So when we started with 200, so this is 100 was the inlet flow rate, the outlet flow rate is 90, so the conversion is about 9.4. But when we increase it to about 360 degrees centigrade, now you can see the 100 moles per hour of propane is the entry, feed rate. At the exit, we almost had 19.9. So what is the conversion? 100 minus 19.9 by 100. So we are able to get to 80% conversion. So in this way, you should be in a position to calculate most of the calculations involved with equilibrium reactions. Of course, if you want to identify what is the composition of the reacting system at equilibrium, instead of looking at all the values, let me look at the results of only this model, because the previous model we did not use the design spec. So at this particular temperature of 359, so the composition of the system at equilibrium is, so you have about 11% propane, 44% ethane and 44% methane. So we were able to calculate this. Now in the same way, how do we calculate, how do we know the equilibrium constant? So we know the composition. You know this composition can only be calculated once we calculate the equilibrium constant. Now let us look at these results, block results. So it will tell you what is the duty? Because the feed is entering at 25 degrees centigrade. Now we need to operate the reactor at around 360. So how much heat must be added in order to increase the temperature? Right? This is the amount. And the mass and energy balances. And this is the phase composition. So, right? And this is the composition of the system once it is at equilibrium. Right? So these are the issues. So with this, I would like to, in fact, you now should be in a position to handle even multi-reaction equilibria. Remember, these two reactor models will be capable of handling only reactions reaching equilibrium. Remember, when you are talking about reversible reactions at equilibrium, we don't have to need the kinetic information, right? So even stoichiometric reactor model and these two reactor models don't require the stoichiometry. So with this, I would like to stop my presentation.